Hey everyone, we're going to look at number 2 in section 3.7. We're computing the derivative, and they say by the chain rule, generalized power rule, some other rules. Again, we're using the rules for differentiating that we've developed up through in this section, the chain rule, which is very important. And this is the function we're differentiating. Notice y is a function of theta. Theta is our independent variable instead of x. And we want to make sure we understand what this notation means. So when we see cosine to the 9th of theta plus 14, what we really mean is this, right? Cosine of theta plus 14th, all raised to the 9th power. In other words, to evaluate the function y, we first take the value of theta, add 14 to it. That's what we do first in the parentheses here. Take that value, plug it in, if you will, to the cosine function and see what we get out. And whatever that output is, we then raise that to the 9th power. In other words, multiply it by itself 9 times. So that's the way that works. And that's important because what we have is a composition of functions here. And right, that's what the chain rule addresses. When we talk about the derivative with respect to x, right? This is the derivative Leibniz notation, or the differential operator. So in other words, we're going to take the derivative with respect to x of whatever's in the parentheses or brackets in this case. And here we have a composition of functions. Notice this is not f times the function g of x. This is f of g of x. So we say f is the outer function and g is the inner function. So we're taking some value of x, plugging into the function g. We're getting an output here. And then that value is plugged into the function f, right? And then we get the output. That's the way we evaluate this function. But we want to know what the derivative is. And so we derived the chain rule, or showed you what that was in the lecture video, right? We take the derivative, the outer function, right, which is f, so f prime, evaluate the inner function times the derivative of the inner function. That's the chain rule, okay? So in this case, the outer function, if I just cover up the cosine stuff in here, the outer function is I'll say u to the 9th power, where u, I'm saying u is my g of x, u is my inner function. Outer function is u to the 9th, inner function u is just cosine of theta plus 14. So I've got outer function and then inner function. So notice the outer function is just u to the 9th. Well, that would just be a power rule. So when we're using the chain rule, when the outer function is just a power function, then you might hear the term generalized power rule. That just says if you take the derivative with respect to x of u to the n, and u here is some function of x, right? In this case, u is cosine of theta plus 14. Then we just take the derivative of the outer function, right? That's the f prime, which would be bring the n down, u to the subtract 1 from n minus 1, right? There's the derivative of the outer function, right? But the inner function is u, times the derivative of the inner function would be du dx, right? The derivative of the inner function. So this is the generalized power rule. It is just the chain rule, specifically where the outer function is a power function. So, same reason, the chain rule, generalized power rule is the chain rule for the specific outer function. That is a u to the n form. So let's do that with this one. The outer function is u to the 9th power. So the derivative is 9u to the 8th. That's the derivative of the outer function. Of course, we evaluate it at the inner function. Okay, at the inner function, cosine of theta plus 14, then times the derivative of the inner function. So I'm going to write derivative with respect to theta of cosine of theta plus 14. So what's the derivative of this? Well, it turns out technically this is a chain rule as well in here. So sometimes we have to take the derivative of the inner function, turns out to be a composition of functions. And here I have outer function cosine, inner function theta plus 14. So it's chain rule again. Derivative of the outer function cosine is negative sine, evaluated at the inner function, which is theta plus 14, times the derivative with respect to theta of that inner function. However, the derivative with respect to theta of theta plus 14 is just 1, right? The derivative of theta is 1, derivative of 14 is 0. So it is a chain rule, but it really has no effect because we're just multiplying this by 1 in a sense. Okay, so cleaning it up, I've got a 1 here, a negative 1 times my sine, and then a 9. I like to bring all my numerical factors up front. So 9 times negative 1 times 1 is negative 9. I've got cosine of theta plus 14 to the 8th power. and then times the sine of theta plus 14. So this is the way I think you can enter it in actually symbolically in Achieve. If we want to go back to that short hand notation, right? So when we see this, we can write it as cosine to the 9th of theta plus 14. I can rewrite the cosine of theta plus 14 to the 8th power this way. So this is a more compact way of writing it. Either way is fine. But that is the derivative. It's not very pretty looking, but that's what we have. Okay, so I hope this helps on this example of using the chain rule.